This is what we're building toward. A messy pile of powder, scanned by an X-ray machine, turned into exact numbers. This sample is 75% of one mineral, 20% of another, and 5% of a third, down to a fraction of a percent. No guessing. No looks like mostly quartz. Actual, defensible, published paper quality numbers. This is called Rietveld Refinement. And by the end of this series, you'll be able to do this yourself, for free, using a piece of open-source software called Profex. I'm going to start from absolute zero. If you've never heard the words unit cell or diffraction pattern, you're in the right place. Here's the roadmap for this series. We're going to build understanding in layers, like building a house. You can't put up walls before you have a foundation. First, we'll cover crystal basics, what a crystal actually is on the atomic level, and why that matters. Second, we'll talk about X-rays, how they interact with crystals to create the pattern we're trying to analyze. Third, we'll finally answer the question, what is Rietveld refinement? Where did it come from? And how is it different from other methods? Then, and only then, we open the software. We'll install Profex, walk through the interface, and run real refinements on real data. A single clean mineral first, then a mixture of 3 phases, then trickier cases like materials with messy crystal sizes or glassy content. By the end, you won't just know how to click buttons. You'll understand why you're clicking them, which is the difference between someone who can run software and someone who can actually trust their results. Before we go further, I want to plant one idea in your head right now. The single most important concept in this entire series. Everything else is just details on top of this. Look at this graph. This is a diffraction pattern, the raw data we're working with. It's a plot of X-ray intensity versus an angle called 2 theta. And it's full of these peaks, some tall, some short, some wide, some narrow, sitting at different positions along the x-axis. Here's the key insight. Every peak in this pattern is telling you 3 completely different things, and they come from 3 completely different physical sources. The position of each peak, where it sits left to right, is determined by the size and shape of the crystal's repeating unit, something called the unit cell. Different materials have different unit cells, so they produce peaks in different places. This is basically a fingerprint of what crystal structure you have. The height, or intensity, of each peak is determined by what atoms are sitting inside that unit cell and exactly where they're positioned. Heavy atoms in certain spots make some peaks tall and others almost invisible. And the width of each peak, how sharp or blurry it is determined by the quality and size of the crystals themselves, plus the instrument you use to measure it. Big, perfect crystals give sharp, narrow peaks. Tiny, strained, imperfect crystals give wide, fuzzy peaks. Position tells you the structure. Height tells you the contents. Width tells you the microstructure. 3 questions, 3 answers, all baked into one graph. Rietveld refinement is essentially a giant, very precise mathematical fitting process that takes a model of a crystal and adjusts that model until its predicted pattern matches your real, measured data. When the match is good, the model has told you the truth about your sample. Quick history lesson, because it actually matters for understanding why this method exists. In the 1960s, a Dutch crystallographer named Hugo Rietveld was working at a nuclear reactor facility in the Netherlands, using neutron beams, not X-rays, to study crystal structures. And he ran into a frustrating problem. The old way of analyzing these patterns required you to separate out each individual peak and measure it on its own. But in a lot of real materials, peaks overlap. They pile on top of each other and blur together, especially with neutron data, where the peaks tend to be wide. Rietveld's idea, published in 1969, was almost stubbornly simple. Stop trying to separate the peaks. Instead, take your entire model of the crystal, calculate what the entire pattern should look like, every point along the curve, all at once, and then mathematically adjust the model bit by bit until the calculated curve matches the whole measured curve as closely as possible, overlaps and all. This was such a powerful idea that it eventually got adapted from neutron beams to X-rays, and today it's used in materials, science, pharmaceuticals, geology, archaeology, battery research. Basically anywhere someone needs to know exactly what's in a powdered sample and how it's arranged. It's now considered the gold standard method for this kind of analysis. And one more thing worth knowing now. Rietveld refinement is a refinement. That word matters. It means you need to start with a reasonable guess of the structure. Rietveld's method doesn't invent that structure from nothing. It polishes a model you already have until it fits your specific data perfectly. Keep that in the back of your mind. It'll matter later. Now, you might be wondering, isn't there an easier way? And yes, there are other methods, and it's worth knowing where Rietveld fits among them, because you'll hear these terms thrown around. The simplest approach is called search match. You take your pattern, compare it against a giant database of known materials, and the software tells you this looks like quartz, or this looks like calcite. That's useful. It tells you what's probably there, but it doesn't give you precise quantities. A step up from that is single peak fitting, where you zoom in on individual peaks and measure their exact position and width. This is genuinely useful for estimating crystal size, but it only looks at one peak at a time and ignores everything else in the pattern. Then there are methods like Lebesgue and Pauli fitting, which are actually close cousins of Rietveld. They fit the whole pattern at once, just like Rietveld does, but they don't use an atomic model for the peak heights. They're often used as a stepping stone to nail down the unit cell and peak shapes before bringing in a full structural model. And finally, full Rietveld refinement, using the complete atomic model to predict not just where peaks are and how wide they are, but exactly how tall every single one should be, based on real physics. This is what lets you extract quantitative phase percentages, refined unit cell dimensions, and microstructure information, all from one fit. Each of these tools has its place, and in real Rietveld work, you often use search match and Lebesgue fitting as early steps before doing the full refinement. We'll see exactly how that plays out once we're in the software. For this entire series, we're going to use a program called Profex, paired with a refinement engine called BGMN. I want to mention upfront, this software is completely free and open source. There's no trial, no license fee, nothing to buy. It was developed by Nicolas Dubelin, and it's used by real researchers all over the world, which means everything you learn here transfers directly to actual professional work. Here's what you'll need going forward. 1. A computer running Windows, Mac, or Linux. We'll cover installation in the next Tools episode. 2. Curiosity, but not prior crystallography knowledge. I'm assuming you're starting from zero, which is why the next 2 episodes are entirely about building intuition. No software yet. And 3. Patience with the math-adjacent parts. I promise I will keep the actual math to an absolute minimum. You don't need to derive equations. You need to understand what each number means physically. So, to recap, by the end of this series, you'll be able to take a raw diffraction pattern like this one and turn it into precise, quantitative answers. about exactly what your sample is made of, in what proportions, and even how good the crystals inside it are. We're going to get there step by step with real software and real data, not just theory. In the next episode, we go back to basics: what a crystal actually is, what a unit cell means, and why a handful of simple numbers can describe an entire infinite repeating structure. See you in episode 2.